Welcome to the first lecture for the third week of the MPP Calculus course. There are two lectures this week, this lecture on implicit differentiation and the second one, which will be a bit longer, on functional forms and functional analysis. Implicit differentiation arises any time when you have a function that cannot clearly and easily be rewritten with y on your left-hand side. For example, this function has y on both sides of the equation. Now, we certainly could move the y cubed term to the left-hand side, but we would never be able to simplify it because we can't take the cube root to get rid of the cube because that y term on the left side is not cubed and so forth. So we need to employ a strategy called implicit differentiation. In order to do this, it helps to reframe y as f of x instead of y. So if you think about it, we could really rewrite this as replacing each of the y terms with an f of x terms. Now, why does that help us? Well, we're able to use the chain rule to perform differentiation on functions whose forms we may not know. That last function we were looking at was a little complex for the first example, so we're going to go with one that is a little more straightforward. So here we rewrite our y's as functions of x, and then we perform a differentiation on each of the terms separately. And it's only this first term that we need to sort of think a little bit carefully about what it means. So we bring down the 3. We still have f of x squared, but now we need to add an additional term because we don't know exactly what this function looks like, but it is something that we can apply the chain rule to. So what we do is we say df of x dx, and since the chain rule is fairly universal, we don't need to know the functional form of f of x to be able to apply it. So I go ahead and now differentiate the rest of the function using the standard rules for derivatives. I'm now going to solve for the derivative dy dx, which is the thing in the end that I'm trying to find. So I move the 1 to the other side. I'll go ahead and switch back to speaking in terms of y. So this is dy dx equals 1. So I'm now going to get the dy dx by itself. I get that dy dx is equal to 1 over 3y squared. And that's my final solution. So here's another example where, again, we would have to take a square root, and that would change the behavior of the function because notice here that this is defined throughout for all values of y and x, versus when we take the square root, we would lose some of those values of x and y for which this function is defined. So we need to differentiate it implicitly, and I'll do it this time without substituting f of x for y. I take the derivative of x as you would expect. I treat the derivative of y exactly the same, except now y is a function of x. So I say that I need to apply the chain rule and get dy dx. Multiply it by the derivative of the outside function times the derivative of the inside function. I can now solve this for dy dx algebraically. I get that dy dx, I'm going to subtract the negative 2x from both sides and divide both sides by 2y, and I get that dy dx is equal to negative x over y. Here's another example. This might be a good one for you to pause the video, try it out on your own, and make sure that you're understanding. All right, so here we go. So we're going to take the derivative of the x cubed as normal, 3x squared, plus we're going to treat y as an implicit function of x. So to do that, I take the derivative of the outside function and I multiply it by the derivative of the inside function. On the right-hand side of the equation, I need to remember that y is a function of x, so I'm going to use the quotient rule here. I'm going to say 6x times the derivative of y plus the derivative of x, 6 times y unchanged. So now we need to solve algebraically for dy dx. I want you to notice that it shows up on both sides of the equation. So I'm going to go ahead and move all of the terms that have dy dx's to the left side and all of the terms without the dy dx's over to the right side. So I subtract 3x squared from the left side. I'm left with 3y squared dy dx. I'm going to subtract 6x dy dx from both sides so that it moves to the left side. I have 6y left over on the right, and remember that I had subtracted 3x squared from both sides. I now need to factor out the dy dx on the left-hand side. I get that dy dx times 3y squared minus 6x is equal to, I don't do anything to the right-hand side, 6y minus 3x squared. The last step is to divide both sides by this 3y squared minus 6x so that dy dx is by itself on the left, and I get that dy dx is equal to 6y minus 3x squared over 3y squared minus 6x. You might at this point say, wow, that's a little messy. And it is. That's okay. You're going to leave the expression exactly as it is. You need to have both x and y in the final expression in this case. If you want to, you can simplify it. You probably should, just because clearly a 3 divides out of both sides. So you'd be left with 2y minus x squared over y squared minus 2x. Here's another example for you to try. Pause the video. All right, here goes. So I differentiate x as normal, x squared as normal, I get 2x, plus I differentiate 3x and get 3. I now am treating y as a function of x, so I need to use the quotient rule to get the derivative for the term xy. I have y times the derivative, x times the derivative of y plus y times the derivative of x, which is just 1, is equal to 0. So notice that these two terms are the derivative of the xy term. I'm now going to try to get dy dx by itself by moving all of the other terms over to the other side. I have x dy dx is equal to negative 2x minus 3 minus y. And now I will divide both sides by x to get dy dx by itself. And we get that the derivative of y with respect to x is equal to negative 2x plus 3 plus y over x. And notice that I just factored a negative 1 out of the numerator in this case. Here's a final example for you to try out. Go ahead and pause the video, give it a shot, and we'll come back. All right, here goes. The first thing I'm going to do that I always do is rewrite this root in terms of the fractional exponent, just because I find it much easier to correctly apply the power rule when I do that. I get 2y squared plus x to the 1/3 times y to the 1/3 equals 3x squared plus 17. And I'm now ready to differentiate one term at a time. Remember that I'm treating y as an implicit function of x, so I take the derivative of the outside function. I get 4y to the first power times the derivative of the inside function dy dx, plus This next term is the product, so I need to use the product rule. I have x to the 1/3 unchanged times the derivative of y to the 1/3. So I need to use the power rule on the outside function. I get 1/3 y to the negative 2/3 times the derivative dy dx. And that's the first of the terms for the product rule, plus 1/3 x to the negative 2/3 times y to the 1/3 equals, on the other side of the equal sign, it's very straightforward. Bring down the 2, I get 6x. The derivative of 17, of course, is 0. Okay, so now I look at this mess and I need to get dy dx, just solve for it algebraically, and I'll get some expression that is a function of both x and y. So I notice that my third term on the left does not include a dy dx. I'm going to move it to the right-hand side. I'm also at the same time going to factor out this dy dx from the first two terms on the left-hand side. So I get dy dx times 4y plus x cubed y to the negative 2/3 times 1/3 equals 6x minus 1/3 x to the negative 2/3 y to the 1/3. So notice that I moved this term to the right-hand side and I factored the dy dx out of each of the two terms on the left-hand side. My final step is going to be to divide the right-hand side by this term so that I get dy dx by itself. I get 6x minus 1/3 x to the negative 2/3 y to the 1/3 over 4y plus 1/3 x to the 1/3 y to the negative 2/3. Now you might be looking at this and asking if you can simplify it in any way, and you really can't. And the reason is that you have these addition terms that you can't simplify any farther. So this is basically, there's nothing to factor out. This is as simplified as it gets. So that's probably the most complex level of implicit differentiation we'll ask you to do for this class. If you had trouble following my logic in that last one, make sure to rewind the video and work it through again on your own until you do understand it. All right, that brings us to the end of the lecture on implicit differentiation. The second lecture will be on functional analysis.